So we're going to go on to chapter 7 here to kind of keep pace. And before I begin, just to make sure everything's good in terms of size on your side, you just say here or yes in terms of that.
Yeah, it looks good.
Okay, thank you. All right, so no, there's no lab today. Again, you can check the announcement I sent out in terms of the schedule and stuff like that. So we're just going to use this to sort of catch up on some of the lecturing and all that good stuff. All right, so today we talked about balancing equations earlier. So in this chapter, we're actually going to talk about sort of different types of equations, different ways to classify equations. And as we will see sort of in this chapter as well, there are many different ways you can kind of classify even like the same reaction. So the same reaction can sometimes be classified in multiple ways, depending on sort of what you're looking at. So let us get started with this here. All right. So as I talked about a little bit earlier, there were sort of really a lot of times three driving forces for chemical reactions to take place. There's the fourth one as well that I don't think I mentioned earlier. But as I talked about earlier, really that formation of a solid or a precipitate is a major sort of driving force for a chemical reaction to take place. So things wanting to come together to make that precipitate, again, is really a driving force for reactions to basically occur. The formation of water, as I talked about earlier as well, is another very important sort of driving force. Transfer of electrons, as we'll talk about very shortly here, is a major sort of broad umbrella of classifications of reactions where transfer of electrons occur, which is a major driving force, and also the formation of gases. So a lot of reactions do involve some type of gases being formed as a result of it. So that formation of a gas really, again, is sort of a driving force to reactions taking place. So there's really sort of two big sort of umbrellas for which reactions sort of basically occur or fall underneath. And underneath these sort of big umbrellas, as we'll talk about here in just a second, are really, two big classifications for which individual, more specific classifications of reactions occur. And those are sometimes referred to as oxidation-reduction reactions, which are usually referred to as redox reactions, which is why it's called oxidation-reduction reactions, redox reactions, and exchange reactions. And really kind of the big umbrella of exchange reactions is double displacement reactions. So these two types of reactions here are sort of your really big categories of reactions. You got your redox reactions, you have your double displacement reactions. And then underneath each of these sort of categories are a bunch of different ways you could kind of classify these reactions in a more specific sort of manner. So for example, double displacement reactions, a very common type of double displacement reaction is a precipitation reaction where we do make that solid. So it's a double displacement reaction, but it also could be classified as a precipitation reaction because you're making a solid. Acid-base neutralization reactions where water is the main product sort of formed, also really a double displacement reaction, but can be classified as an acid-base neutralization reaction, as we will see. Redox reactions, sort of the same deal. Redox reactions involve basically electron transfers. They also can be specifically sort of classified, some of them, for example, as combination or synthesis reactions, decomposition reactions, as we will see in this chapter as well. So these are really these two guys here, that redox reactions, that double displacement reactions, they really are sort of those big categories for which underneath we have a lot of more specific classifications that we could do for individual reactions. So let's talk a little about first, I think redox is sort of where we're going first on this. So oxidation reduction reactions involve really two things. They involve an oxidation occurring, and they also involve a reduction occurring. The good news about that type of reaction is if you can figure out, for example, if one thing's being oxidized, the other thing has to be reduced. So they always happen together. So if something gets oxidized, there is something that's going to get reduced at the same point. So really what does these mean? We're going to see here in these couple of definitions, but your basic definition of sort of oxidation is when something loses electrons. And in most general chemistry sort of applications, that's usually the definition that you go by. While reduction is usually when somebody gains electrons, as we will see. And those are your two sort of really main definitions of them. And like I said, in general chemistry, that's typically what you sort of look at in terms of those types of reactions. So what way you can remember that is sometimes people remember Leo the lion goes grr. Loss of electrons is oxidation. Gaining of electrons is reduction. Sometimes people remember oil rig. Oxidizing is losing. Reducing is gaining. You can put them both together and, put Leo the lion on the oil rig, and then you don't have to choose, and you have them both there together. So oxidation, as we see here, is sometimes viewed as losing electrons, which is the main definition we'll probably see in this class and probably in 1A as well. But other definitions are what we see here of oxidation is the gaining of oxygen as you go from reactants to products, and also the loss of hydrogen as you go from reactants to products. So those are two sort of definitions, other definitions of oxidation that involves oxygen and hydrogen, which is sometimes used a lot in organic chemistry, especially when there's a lot of non-metals involved. So what does it mean if something sort of loses electrons? So if we lose electrons, if you just think about it, that means that something is going to get more positive. And what we mean by that is the oxidation state will get more positive. So sometimes to figure out oxidation reductions, you can make a very simple number line. And usually to the right of 0 is a positive numbers. Usually to the left of 0 is negative numbers. So when something goes through oxidation and it loses those electrons, it is moving in the positive direction. And that is when something goes through oxidation. When somebody gains electrons, which is what happens with reduction, they become more negative because they have more electrons that they've gained. So if you go in the opposite direction, going towards the negative side, that is usually involves reduction happening. So when we talk about oxidation states is not necessarily the charge that we normally associate with an element. It is technically the charge the element would have if all the electrons were completely transferred. And oxidation states are sometimes different than actually the charge that we normally associate with things when we talk about ionic compounds. So just briefly, let's just kind of talk a little bit about how to identify oxidation numbers and some of the rules which will be helpful to help you kind of determine what you're looking at. So for example, here, if you have anything that is uncombined in its natural state, it has an oxidation state or number of 0, basically. So oxidation number of 0. They're sometimes called oxidation states as well. Now, oxygen is a really good place to start. Oxygen is typically -2 in terms of its oxidation number. Unless it's peroxide, then it's -1. But probably most of the time you'll see it will be -2. Things with their normal sort of charges are monatomic ions. That's what their oxidation number is. So if you had iron 3, it would have a +3 oxidation state. So these are sort of the pretty easy ones to sort of remember. Hydrogen is always +1 when it comes first, -1 when it comes after a metal. So these are sort of Cliff Note versions of how to figure out oxidation numbers. So let's kind of put these guys to test in what we're looking at here on this slide. So if we look at this slide here, our sodium is going from no oxidation state, just solid sodium, to +1. So what that means, again, if you look at the number line is, it is starting at 0 and it is heading to +1, which is moving in this direction. It is going through oxidation. Our iron that goes from +2 oxidation state to +3, again, +2 would be like here. And then it's moving to +3, which would go to the right, which would also be going through oxidation. And if you look at something with -2 to 0 would be the oxidation state here. -2 would be like over here, heading towards 0 is in this direction. Again, also going to the right and becoming more positive. So all of these guys are examples of things that are going through oxidation. They're all getting more positive or less negative, whichever way you want to look at that. And again, literally a number line is a great way to figure that out. Just draw where you start, and either you're going to go to the right, which is oxidation, or you can go to the left, which is reduction. And that's a very good way to sort of figure out, is that thing going through oxidation or reduction? Question on those there. Now, reduction, as I mentioned before, is usually the most definition that you'll use is our gaining of electrons. But again, if you're dealing more with nonmetals and stuff, it also can mean oxygen that you're losing from reactants to products, or hydrogen that you're gaining from reactants to products. So again, these are two definitions of reduction, but for our purposes, and like I said, most of your general chemistry purposes, this definition here is what you're going to come across. And again, we can use our number line here to figure things out. If we look at calcium, is starting at +2. Calcium metal by itself has a 0 oxidation state. So again, +2 would be here. Going towards 0 is going to the left, and that means it's becoming more negative and going through reduction. Iron is going from +3, which would be like over here, to +2, which is going to the left as well, also going through reduction. Our oxygen is going from 0 to -2. So 0 is here, again, going to -2, which is to the left, which means it's going through reduction. So again, a very kind of straightforward, simple way to figure out what's going through oxidation and what's going through reduction. Now, in general, when we talk about an ionic compound, we already kind of know what's going to happen there, right? Our metal is typically the one that will lose electrons, and our nonmetal will gain electrons. And that's the idea behind an ionic compound. And we know that the metal will always be the thing that gets oxidized. The nonmetal will be reduced. When you have metal and nonmetal together, that is always the situation that occurs. And that's really the basis of an ionic compound coming together, is that formation of the electrons being transferred. And again, one of those driving forces for a chemical reaction basically to occur. So as I mentioned, oxidation state or number for anything in its natural uncombined state are 0. So that goes for things like O2 is going to be 0, Br2 is going to be 0. However it comes, if it's just by itself naturally, not attached to anything at all, it has a 0. And that's the idea that we talked about. Like if you pull just sodium metal like we see here off of the periodic table, it is a solid. It has no charge. If you pulled calcium metal off the periodic table, it has no charge. If you had nitrogen gas the way it normally comes, not combined really with any other element, it's going to be 0 in terms of its oxidation state. So things, again, in their natural state, uncombined, will always equal 0. Any questions on redox, oxidation reduction so far? By the way, sometimes when we talk about oxidation numbers, just to sort of show you, what's happening, When we look at something like nitrate, which we saw earlier, a polyatomic ion, which is NO3 minus. Now, when we would try to figure out the oxidation states of each of these guys, oxygen is a really good place to start. It is always -2. There are 3 of them, which gives you a -6. The overall charge on this thing is -1. That means when we add up all of the oxidation numbers together for all the elements that are there, we add up all their individual sort of oxidation numbers, they do need to equal the charge that we see on the ion, or 0 if there is no charge. So in this case, to get us to actually -1, the nitrogen in this case takes on a +5 sort of appearance, if you will. +5 and -6 gives us -1, which is why the charge on nitrate is -1. And you may say to yourself, but didn't we learn with naming that nitrogen makes a -3 charge? And the answer is yes, we did. And the answer is some things, especially nonmetals, when they are hooked up with other nonmetals, they sometimes can take an oxidation state that is different than what they would take when they hook up with a metal. And that's because of those periodic trends that we talked about. When a metal and nonmetal get together, the metal's like, take my electrons. The nonmetal's like, no problem, I'll take them. So we get that full transfer of electrons. And those sort of charges that we talked about earlier are with that in mind. But when we hook up together here, like we see here, a nitrogen with 3 oxygens, those are all nonmetals, right? And they are right next to each other on the periodic table, which means, as we talked about with our periodic trends, they have very similar trends, which means they don't want to give away the electrons. They both really kind of want the electrons. And that's why, as we talked about with bonding, something like nitrate will actually share electrons, right, between the nitrogen and the oxygen. So in that sharing of electron situation, our nitrogen that we normally think about as a -3 charge actually takes on a more positive performance or persona there, because as it is bound here to those 3 oxygens, basically those oxygens are more electronegative, which means the oxygens are going to pull the electrons away from the nitrogen, and it's going to take on a +5 sort of role, rather than when, say, a aluminum and a nitrogen come together and it gains those 3 electrons completely, it takes on a -3 sort of role. So oxidation state is not perfectly exactly the same thing as charge, but it's sort of the charge that elements will take in their particular arrangement. And the difference between, say, the nitrogen on the left here, nitrogen on the left is an ionic compound where we get that complete transfer of electrons, while the nitrogen here on the right is more in a covalent bond sharing electron situation, and it's able to take on a more positive sort of oxidation number. Any questions on that? So we could definitely use oxidation numbers to help us figure out what's going on in terms of, is something sort of more being oxidized or being reduced? And again, that number line is a really good way to kind of do that. Now, as I mentioned before, redox reactions, again, are sort of the big umbrella for which these more specific types of redox reactions occur. So all these ones can be classified as these type of reactions on their own, but they also are, again, classified under the big sort of umbrella as redox reactions. So oxidation reduction occurring here. So let's take a look first at a synthesis reaction. And in a synthesis reaction is also sometimes referred to as a combination reaction. And both a synthesis and a combination reaction, basically the generic formula for it is A plus B makes AB. So basically 2 things make 1 thing. So combination, synthesis, basically putting together 2 things to make 1 thing is your classic synthesis reaction. So again here, 2 things make 1 thing, synthesis reaction. 2 things make 1 thing, synthesis reaction. Again, 2 things make 1 thing, a synthesis reaction. Now, this guy and all these guys are also at the heart of it, redox reactions. So if we look at, for example, this first one, oxidation state of carbon by itself uncombined is going to be 0. Oxidation state of oxygen by itself uncombined is going to be 0. In this situation, again, if we were to dissect the oxidation numbers that are going on here, we would start with oxygen, which is -2. There's 2 of them, gives you -4. The overall charge on CO2 is 0. To balance that out, our carbon in this case is actually taking a +4 oxidation state, and our oxygen is -2. So we do see changes in the oxidation state, which indicates it's a redox reaction. And if we figure out what is going on, our carbon is starting at 0. And on the other side, it ended at +4. So it is going to the right, which means this is going through oxidation. So it is our carbon that is going through oxidation here. And by default, what that means is our oxygen is going through reduction. You could also figure it out for the oxygen. If you start with the oxygen, it is starting at 0. And it is ending at -2, which means the oxygen is going in this direction. And that means that the oxygen is becoming more negative or going through reduction. So the oxygen here is going through reduction. So this is also, again, a redox reaction that is happening. And it also can be classified as a synthesis or combination reaction as well. Same thing if we come down here to our sodium chloride formation. Sodium in its natural state is 0. Chlorine in its natural uncombined state is 0. When those two guys get together, that is when they actually do gain charges. The sodium on the right-hand side is +1. The chlorine on the right-hand side is -1. So again, if we apply our number line here, sodium is starting at 0 and ending at +1, which means it is going in this direction. So the sodium is going through oxidation. The chlorine is starting at 0 and ending at -1, which is going to the left, which means it is going through reduction. And that's what we would expect. A sodium, which is a metal, we would expect it to lose electrons, which means it should be going through oxidation, while the Cl2 is gaining electrons because it's a non-metal and it is going through reduction. So again, all three of these reactions can be classified as synthesis or combination reactions. They also can be classified as redox reactions under sort of the big umbrella of redox. Question on that there. And that's what we see here. And also, if we wanted to write these things to represent what's happening, we could write something like carbon is basically going to our carbon with a +4 in this particular case. Again, losing 4 electrons here in this particular case. And this would be known as the oxidation half reaction. Electrons on the product side, like they're being lost, is for our oxidation, while oxygen would go from that +4 electrons, making 2 oxygens with a -2 charge here. This would be our reduction half reaction. And the electrons on the reactant side is a reduction half reaction. So sometimes we could break this up even more specifically into what are referred to as half reactions. They're a half reaction because if you add them back together, they give you the overall reaction that is present in that particular case. Here is our water example. Again, if we go through our oxidation numbers here, our hydrogen in its natural state is 0 on the left-hand side. Oxygen is 0 on the left-hand side. When they combine, hydrogen is +1, oxygen is -2. So again, hydrogen starting at 0 ending at +1, so it's going through oxidation. Oxygen starting at 0, ending at -2, going through reduction here, or O2. And again, they always occur together. So if you were only able to figure out that hydrogen is going through oxidation, by default, the oxygen would have to go through reduction. Any questions on that particular one there? And then there's our sodium chloride there. I think that we did the example earlier of, let's see here. It is not. So it's those rules in terms of how do you know the oxidation number? It's those rules that I just wrote a little bit on that first slide. Again, when you're trying to assign oxidation numbers, anything in its uncombined form, the way it naturally comes by itself, one element by itself, has an oxidation number of 0. So that's how we know that. So that's this guy right here. Sodium all by itself, just straight from the periodic table, has an oxidation number of 0. Chlorine all by itself, not combined with anything, has an oxidation state of 0. Now, when things come together, that's when they get their charge. And especially anything that is basically an ionic compound will have its normal charge. So sodium is always +1 when it comes together with a nonmetal, and chlorine becomes -1 when it comes together with our metal in this particular case. Other things in terms of assigning oxidation numbers is oxygen is a good place to start. Oxygen is typically -2. Hydrogen is typically +1 in terms of its oxidation numbers. So those are sort of how we get to those oxidation numbers, by following those sort of rules. So again, oxidation numbers may not match exactly what we think about in terms of ionic compounds and the charges that things have. And sometimes they are the same, but sometimes they're different. They definitely will be the same if you have an ionic compound. So if you see an ionic compound like we see here with sodium chloride, everybody will have the normal charges we would associate with it. So for example, here, again, as we talked about earlier, if we look at our chlorine is starting at 0 and again ending at -1, so going through reduction in that particular case, and that means that the sodium would go through oxidation. Any questions on that there? Okay. Now, you'll sometimes see, since people talk about oxidation and reduction, you'll sometimes see words like oxidizing agent or reducing agent. So these definitions are a little confusing sometimes for people when they say, hey, what is the oxidizing agent? What is the reducing agent? The thing that is the oxidizing agent is actually the thing that goes through reduction. So the substance that goes through reduction is what is referred to as the oxidizing agent, while the reducing agent is the substance that goes through oxidation. So you may ask, why did they call it that? Well, the reason they call it that is, for example, here, if we look at our sodium, as we determined, our sodium is going through oxidation, which means it is going to lose electrons. And when it loses electrons, it allows somebody else to gain electrons. And when something else gains electrons, it goes through reduction. So it is referred to as being the reducing agent because it is going through oxidation. While the chlorine, as we just talked about, the Cl2 is going through reduction, which means it's going to gain electrons. In order for it to gain electrons, it has to cause something to lose electrons. And when something loses electrons, that is something that's going through oxidation. And that is why this was referred to as the oxidizing agent. So we probably won't deal too much with reducing agents and oxidizing agents, but I do, in terms of those names, but I do want to mention it because sometimes it does pop up when you start talking about this type of reaction. So if you're asked about the agent, it's the opposite of the name. So if you want the reducing agent, that is the thing being oxidized. If you want the oxidizing agent, that is the thing being reduced. And again, any questions on that part of it there? Okay, so these are synthesis or combination reactions, which basically you put two things make one thing. Then they are also referred to as redox reactions because ultimately what's happening is we're getting these sort of transfer of electrons that are occurring. Another type of redox reaction that is known is a decomposition reaction. And really a decomposition reaction is almost the opposite of a synthesis. In a synthesis reaction, we put it together. In a decomposition, we break it apart. So the general form for a decomposition reaction is we start with one thing and make, two or more things, basically. So if we run an electrical current over water, we will break it apart into hydrogen gas and oxygen gas. One thing makes two things. Lead 4 oxide breaks apart into lead and oxygen. Aluminum nitride breaks apart into aluminum and nitrogen. These are all examples of decomposition reactions. One reaction making one thing making multiple things. So synthesis, combination, put it together. Decomposition, basically break it apart. And as you might imagine at this point, and we will see here, each of these reactions as well, in addition to being able to be classified as decomposition reactions, they are all redox reactions as well. So these are all redox reactions that are happening as well. So let's take a look at those oxidation states so we can see what's going on here. So if we do our oxidation states for our water being broken apart, again here, oxygen being -2, hydrogen being +1. On the other side, we actually make the element form of each of those guys. And in their natural states on the product side, they both have an oxidation state of 0. So again, looking at the hydrogen, it is starting at +1, which would be like here. And it is ending at 0, which means it is going to the left. Going to the left there means reduction because it's getting more negative. And we would know that the hydrogen here is going through reduction. Now, if we look at the oxygen, oxygen is starting at -2 on the left, and it's ending at 0, which means it is going in the right direction there. And that means it's becoming more positive, are going through oxidation. So our hydrogen here, which is really H+, it is going to H2, is going through oxidation in this particular case. While our oxygen, which is here, which is really oxygen with a -2 charge, is going to oxygen with no oxidation state. So again, this guy is our oxidation reaction, and this is our reduction reaction. And in terms of what we've been talking about, because this O2- is going through oxidation, this would be our reducing agent. The H+ here would be our oxidizing agent as it is going through reduction. Question on that one there. So again, you can see by looking at the oxidation numbers, decomposition, one classification, but a decomposition reaction is essentially a redox reaction happening as well. Here's the other few that we see on that sort of example. Again, this is lead 4 oxide. So the oxidation state of our lead starting out is +4, which would be over here. Our lead on the other side is by itself, so it is 0. So it goes from +4 to 0. So the lead here is going through reduction. While if we look at the oxygen, oxygen is -2 here and going to oxygen by itself, which is 0. So our Oxygen is starting at -2 and ending at 0, going through oxidation in this particular case. And we had one more. And same thing here with our aluminum nitrite and our nitrogen. This is an ionic compound, so everybody has their normal sort of charge or oxidation number. So aluminum here, starting at +3, which would be like here. On the right hand side is aluminum by itself, oxidation state of 0, going to the left, becoming more negative, going through reduction, which is our Al. And our nitrogen starting at -3 and ending at 0, going to the right, going through oxidation in this particular case. And this would be our nitrogen going through that. Any questions on any of those three there? A, how to determine their oxidation numbers and what is being oxidized and what is being reduced. So again, overall, as you can see, big category, redox reactions. More specific classification for this particular type of reaction is a decomposition where one thing breaks apart into multiple things. Another sort of classification for reactions that are redox reactions are what are referred to as single replacement reaction or single displacement reactions. And let's take a look at some of those as well. So in a single replacement reaction, there's really, whoops, come back. There's really this sort of general formula. And when we look at it, the way you could recognize it is you have this guy here, which can be a metal or a non-metal. But the key about this guy over here is it has no charge. So it's either the metal by itself, it's the non-metal by itself. It will start with an oxidation state of 0. I'll kind of write up there. The other thing that you'll have in this type of reaction, which is a single replacement reaction, is you will have an ionic compound. So you'll have a positive guy and a negative guy. So that is classically the way you could recognize a single replacement reaction. You should have either a metal by itself or a non-metal by itself, not combined, oxidation state of 0. And you should have a ionic compound that's going to react with it. And what happens is it kind of depends. So if C is a metal and it reacts with our ionic compound, although this metal, when it starts, has no charge, because it is a metal, metals typically will become positively charged. So it will come in and kick out the positive guy in that ionic compound. And when it does, it's at that point that the C in this example will gain a positive charge, and you will make a new ionic compound, positive and negative. And the original guy that was positive will come out by himself, uncombined, with a 0 oxidation state as well. So this is what is referred to as a single replacement reaction. Metal comes in, kicks out the positive guy, and we're left with a new ionic compound and the metal that comes out by itself. Now, if this C was a non-metal, so let's just deal this up here. Let's get rid of that real quick. So let's say, for example, that we actually had a non-metal that's happening. So we'll say this guy is a non-metal. Non-metals, again, by themselves have no charge, but when they do gain a charge, they do become negatively charged. So this case, he's going to come in and actually kick out the negative guy, and he's going to make a new compound. I guess I should have stole that. And the new compound is going to be the A that's positive, and our C will now become negative, and then our non-metal guy will come out with no oxidation state. So again, you'll form a new ionic compound and a non-metal with a 0 oxidation state. Now, in order for this reaction to take place, whatever is coming in needs to be more reactive than what it's replacing. So whatever is coming in needs to be more reactive than what it replaces. Now, if whatever is coming in is less reactive, then the reaction will not take place. So in order for this reaction to take place, whatever is coming in needs to be more reactive than what it's replacing. Any questions on that so far here? So just to sort of see are a couple examples down here. These are all examples of a single replacement reaction. So again, here our copper has no oxidation state. This is a positive negative guy. So that's the way you can recognize as a single replacement reaction. And the copper is going to come in and kick out the silver. Silver here has a +1 charge. When it comes out on this side, no charge, no oxidation state. Then the copper will actually gain a charge and hook up with the nitrate. And the copper here becomes +2. Our nitrate becomes -1 in this particular case. So this is a single replacement reaction. As you can probably see here, also a redox reaction happening. Copper going from 0 to +2, silver going from +1 to 0 on the other side. Same thing here. We have our magnesium, which has no oxidation state. We have hydrochloric acid, which is essentially a positive and negative guy. Same thing's going to happen here. Magnesium is going to come in and kick out our positive guy. When hydrogen gets kicked out, it becomes hydrogen gas, which means you would see bubbles occurring and stuff like that. Also has an oxidation number of 0. We make a new ionic compound, positive and negative. So again, both of these are examples of single replacement reactions. There are also, as we will see here and been talking about, also really redox reactions that are occurring as well. Any questions on that? So let's take a little closer look at those redox aspects of it. So as I mentioned before, if we kind of look at what's happening here, if we look at the copper first, again, oxidation state of copper by itself is 0. So it is starting at 0. On the right-hand side, copper becomes +2. So going to the right, going through oxidation, and that would be our copper. If we look at the silver, silver started at +1, which would be over here, and it is ending at 0, which is going to the left, and that is reduction in this case, and that is silver with a +1 charge. Now you may ask yourself, what's the deal with nitrate? And the deal is nothing. It is -1 on the left-hand side. It is -1 on the right-hand side. It is essentially not doing anything. It is what is sometimes referred to as a spectator ion. It's basically just there to watch. It's really there to balance out the charges of everything, but it's really not participating in what's happening. So if we were to break this down, really what is happening here is we have our copper that is going to our copper with a +2 charge. And it is going to be losing 2 electrons. And on the other side, we have silver that's going to be gaining 2 electrons and making 2 silvers on this side. This is, again, our reduction half reaction. This is our oxidation half reaction. Again, we know that because oxidation, electrons being lost on the product side, reduction, electrons being gained on the reactant side. And if you kind of write them together, overall what's happening is the copper plus the couple of silvers is making our copper with a +2 and our 2 silvers with no charge. This is what is sometimes referred to as the net ionic equation that's happening. It really gets to the heart of the matter of what really is happening when you put these things together. The copper is giving up its electrons. The silver is saying, thank you very much, and picking up those electrons in this sort of reaction. Again, the nitrate here is really just a spectator ion, not really participating in, the overall reaction that's taking place. Any questions on that there? And here as well, again, a redox reaction happening. We could follow our same sort of guy. Magnesium starting at 0, ending at +2, going through oxidation. Hydrogen here starting at +1, ending at 0, going through reduction, which is our hydrogen. Again, in this case, the chlorine, nothing's happening with it, really just a spectator ion, not much happening, no oxidation reduction happening. It's just those two things, the magnesium and the hydrogen, that's basically going through oxidation and reduction. All right, any questions on any of that so far there? So again, these are single replacement reactions. Just to show you a non-metal one, let me find somewhere I can scribble here. So for example, if we took, let's say we took chlorine plus our, say, sodium iodide. Again, here the chlorine is 0. This is an ionic compound, which is a positive negative guy. Chlorine, which is a non-metal, doesn't have a charge yet, but when it does, it's negative, which means it would come in and kick out the iodide. When it comes together, the sodium and the chlorine make a new ionic compound, sodium chloride, and the iodide comes out by itself. And probably do a little balancing, a 2 there and a 2 there. And this would be a single replacement reaction involving a halogen. And again, this reaction would take place. So you may be asking yourself, how do you know if perhaps a single replacement reaction will take place? There's actually something known as an activity series. And basically in an activity series, it's a bunch of elements, and usually hydrogen is somewhere there, and a bunch of elements kind of underneath it. And when you look at an activity series, anything that is higher on the list will replace anything lower on the list. So for example, if we looked at this list, what we would see is magnesium would be higher on the list than hydrogen, and this reaction would take place, and we would see this reaction take place. Now, if you try to do the same reaction with copper metal, and this list would be provided for you if you needed it, but if you looked at copper metal, you would actually find it lower on the list than hydrogen, which means when this guy comes in to replace this reaction will not take place, and you will not get a reaction that will actually take place. So if you have an activity series given to you, that's essentially how it works. It's kind of a list of elements, and anybody sort of higher on the list will replace somebody lower on the list, but somebody lower on the list will not replace anybody that is higher on the list. Any questions on that? Now, you may also ask yourself, what's the deal with our nonmetals? And our nonmetals, actually group 7 on the periodic table is the activity series for the halogens. So if you look at group 7 on the periodic table, fluorine, chlorine, bromine, iodine, reactivity increases this way, which means, as we just did in this example, chlorine is higher in group 7 than iodine, which means this reaction would take place. So the chlorine would replace it. Now, if you flipped it around and went with iodine plus some sodium chloride, this reaction would not take place because iodine is lower on the list than chlorine. So again, group 7 on the periodic table is its own activity series for halogens. And again, anybody that's higher in group 7 will replace anybody lower in group 7, and the single replacement reaction would take place. Again, opposite of that is what I just did there at the end. If it's lower in group 7, it will not replace anybody higher in group 7. Any questions on single replacement reactions? Probably for the most part for us, we'll assume probably most of those will work, but there really is sort of a activity series or something like that that will help you decide whether or not this reaction will actually take place. Another type of redox reaction is a combustion reaction. So let's talk about those guys. Go through all that. There we go. Now, I will say that a combustion reaction, there's kind of two types of combustion reactions. And the simplest definition of something that's a combustion reaction looks just like this. Pretty much you need O2 involved. So anything that O2 is involved in can be considered a combustion reaction. Most of the time, though, people always a lot of times are thinking about this type of combustion reaction, which is sometimes referred to as an organic combustion reaction. And an organic combustion reaction, like we see on the bottom reaction on the screen, it is usually an organic compound. And what that means is it's something with carbon, hydrogens, or oxygens, plus O2 makes CO2 plus water. So as it says in red, this is always what you get when you do a organic combustion reaction. So methane is an organic guy. It contains carbon, hydrogen, no oxygen in this case, but pretty much carbons and hydrogens. And we always get CO2 and water. But the basic general definition of combustion is you pretty much just need O2 present. And that usually is enough for it to be sort of classified as a combustion reaction. So if we look at this first one here, this is technically a combustion reaction because it involves oxygen. Now, you may also say to yourself, is it some other type of reaction? And the answer is yes, it is. So if we look at this guy closer, in addition to it being a combustion reaction, we also see it is a redox reaction. Again, our magnesium is losing electrons and becoming more positive, while our oxygen is gaining electrons and becoming more negative. So it is a redox reaction happening as well. So you could classify this reaction as a redox reaction, technically. You could also classify this probably as a combustion reaction because it involves oxygen. But most people may also classify it one more way. I have two things that make one thing. Some people may classify this as well as a synthesis or combination reaction, like we saw earlier. Probably most people would probably classify that as a combination or synthesis reaction. Again, if it does fall into the combustion window, it is under the big umbrella of redox reactions as well. So this is a very good example of, like I was talking about earlier, that you could be looking at the same reaction and you literally can classify it multiple ways depending on sort of what you're looking at. So in this particular example here, we could classify it as a synthesis or combination reaction. We could classify it as an a combustion reaction, and we could classify it as a redox reaction, which it really is as well. And here again is our organic combustion reaction, which, as you could also see here from the oxidation states, also a redox reaction that's happening. So in this particular case, we have carbon going from -4 to +4 in this case. So again, just to give you an idea of what's happening there so you can visualize it. Carbon again starting at -4, which is way over here, and ending at +4, which is going in this direction. So again, it is going through oxidation, as I mentioned, and our oxygen going from 0 to -2, going through reduction. So this one could most often would be classified probably by most people as a combustion reaction, but can also be classified as a redox reaction as well. Any questions on that there? All right, so let's take a look at this one here. The reaction between hydrogen and oxygen to form water can be classified as could be classified really as we got two things that make one thing here. So this could be a synthesis. We have 0 oxidation state, 0 oxidation state, +1, -2 could be a redox reaction. And I guess technically speaking, it's got oxygen, so it could also be a combustion. So it would be D in this particular case as a possible answer here. Any questions on that there? So why don't you take a second and figure out which is being oxidized in this reaction. All right, so let's take a look here. So by itself on the left here, oxidation state going to be 0. That's Br2, which is how it naturally comes uncombined, also going to be a 0. That's a metal and a non-metal, so when they come together, it's going to make an ionic compound. So in this case, the oxidation states will be the same as the charge. So this is cobalt-3 bromide, which means the cobalt here is +3, the bromine is -1. So if we do our little number line here, and we look at the cobalt starting at 0 and ending at +3. So it is going through oxidation, the cobalt. While the bromine here is starting at 0 and ending at -1, it is going through reduction here, which is our Br2. So to answer the question, the substance that is being oxidized should be our cobalt. Question in this case. Okay. Now, what is our reducing agent? So this is the one we just did. Again, 0, 0, +3, -1. As we just determined, our cobalt becoming more positive is going through oxidation. Our Br2 is going through reduction. Now, remember here, this is not asking you what is being reduced. This is asking you what is the reducing agent. So the reducing agent is the substance that gets oxidized, while the oxidizing agent is the substance that gets reduced. So with that in mind, since cobalt is going through oxidation, the cobalt would be the reducing agent. And just because bromine here is going through reduction, that means that the bromine here would be the oxidizing agent. So remember, when you're asked about those agents, they are opposite of the name. So the reducing agent gets oxidized, the oxidizing agent gets reduced. And that means, to answer our question here, the reducing agent should be our cobalt in this particular case. Question on that there. Okay. So why don't you do this? Why don't we do all this? Why don't we figure out what is going through oxidation? What is going through reduction on this one? What is the oxidizing agent? And what is the reducing agent on this particular one? So see what you come up with for that. And then we'll talk about it. Okay, so let's take a look here. So again, we have the copper not combined. So just by itself, has no charge, zero oxidation state. Same thing for our oxygen. Again, it is not combined with anything else, no other element. It's how it naturally comes. Also has an oxidation state of 0. This is copper, by the way, copper Roman numeral 1 oxide here. That means that the copper has a +1 charge. Oxygen has a -2 charge in this particular case. So now we could kind of, again, use our number line, if you like, to help you figure out what is going on. We'll start with the copper. I don't want to say carbon for some reason. Copper. Copper is starting with 0. And on the right-hand side, it ends up at +1, which is going to the right-hand side, again, becoming more positive. So it is going through oxidation, would be our copper. Our oxygen is starting at 0, and it is ending at -2 on the right-hand side, and that is going through reduction. So the thing that is going through oxidation is the copper. The guy going through reduction is the oxygen. So now when we get to our oxidizing agent is the substance that gets reduced. So our oxidizing agent would be O2. Our reducing agent is the substance that gets oxidized. So that would be our copper in this case. So to answer the question that was asked, it is oxidizing agents O2, so it should be B here. Question on identifying that there. Now let's classify the following redox reaction. So what ways can we sort of classify this? Again, maybe more than one classification, maybe just one classification. So let's see. Let's start with a synthesis reaction. So synthesis reaction means we take 2 things and make one thing. So I would say that qualifies. So A looks okay. Is it a decomposition reaction? A decomposition reaction is we start with one thing and make multiple things. That does not look like the case here. Single replacement, we have one thing with no charge and an ionic guy. where the one guy comes in and replaces. And that does not look like this situation here. There is no ionic compound there, so it can't be that. And combustion needs at minimum oxygen involved, and I don't see any O2, so it can't be that either. So it looks like the best classification here is a synthesis or combination reaction, or again, you could classify it again as a redox reaction. Any questions on that there, on that one? Okay, and if we had to classify this one, take a second and go with the classification on that. Okay, so let's take a look and see if we can determine. We'll start with the first one, which is a synthesis. So again, synthesis or combination, two things make one thing. Does not look like the case here, so I would not say so. Decomposition, as we talked about, is one thing that breaks apart into a couple of things. Also doesn't look the part. Single replacement is one thing plus an ionic compound. So I got one thing by itself, so that's good. This is nitric acid, which is a positive negative guy. Remember, if you have an acid, pretty much the cation is H plus, and there's a negative guy, right? So again, you can think of acids as a sort of ionic compound, and that means that we should have C, perhaps. Combustion needs some O2. I don't see any O2, so that doesn't look good. So it looks like C here would be probably the best answer. Question on that. And again, you could classify that one as either a redox reaction. Most people would probably classify it as a single replacement reaction, but technically could be classified both ways. So far in this chapter here, we talked about sort of the big umbrella of redox reactions. Again, underneath that big umbrella redox reactions involve reactions which are synthesis reactions, decomposition reactions, combustion reactions, and single replacement. So again, you can think of it as the redox is the big umbrella, big category, and then more specific classifications, those four kind of more specific classifications underneath it. And that leaves us the last sort of big category, which is really our double displacement reactions. And obviously, because of time, we will stop here for today. But we'll talk about what those are and all the kind of specific classifications that fall underneath that. Any questions on anything we talked about today? So again, a reminder, we did move around a few things this week and next. I did send out an announcement, so make sure again that you refer to that so you know what's going on. So on Wednesday, we will continue lecturing chapter 7, and we will be doing an experiment, which should be, I think it should be what's scheduled. So I think it's chemical reactions. So we will be doing that. Again, the online pre-lab should be due at that point. I haven't had a chance yet because I sort of forgot to do